What kind of microscope do we need in order to see atoms? An optical microscope won't work. The resolution of an optical microscope is limited by the wavelength of light used, as features smaller than this will be impossible to resolve. A scanning tunneling microscope will instead exploit the quantum behavior of electrons to perform observations. As electrons are smaller than the atoms being probed, this will make the observation of individual atoms possible. Scanning tunneling microscopes use a sharp conductive tip to probe the surface of samples. These end in a point only a few atoms wide. First, a potential difference is applied between this tip and the sample itself. Subsequently, as the tip approaches to within a nanometer of the sample surface, it will become possible for electrons to move between the tip and the surface in a process known as quantum tunneling, generating a current. What is quantum tunneling, and why is it important? According to the laws of classical physics, electrons shouldn't be able to cross the gap between the tip and the sample. This is because it requires energy to remove the electrons from the surface of the metal tip. The energy needed to move the electron from the surface of the metal tip to freely existing in the vacuum between the tip and the sample is called the work function, here represented by the symbol phi. We can think of this as an energy step the electron must climb up. Only afterwards is it possible for the electron to fall down to occupy the lower energy states in the positively charged sample. In the scanning tunneling microscope, there is no source to provide the additional energy required for the electron to pass over the barrier. Therefore, it cannot cross the barrier using the classical path. However, quantum tunneling allows the electron to bypass the barrier, travelling through the forbidden region to occupy a lower energy state on the other side. The rate at which tunneling occurs depends on both the work function of the material, which determines the height of the barrier, and the tip-to-sample separation, which determines the width of the barrier. Here notated as omega, this separation will normally be between 0.4 and 0.7 nanometers, the size of only a few atoms. The barrier illustrated is for a simple case, where both tip and sample materials have the same work function. The tunneling current is highly sensitive to the gap width. It will increase as the gap width is reduced. Consequently, the scanning tunneling microscope can detect tiny changes in the surface topography. In most systems, a computer adjusts the tip height so as to maintain a constant tunneling current, while scanning the tip across the surface. By tracking the movements of the tip, a trace which approximates the structure of the surface can be obtained. Scanning tunneling microscopes are generally built to operate in ultra-high vacuum and at temperatures near 0 Kelvin. The vacuum prevents contamination of the sample. Low temperatures limit the movement of the atoms in the sample due to thermal kinetic energy. Under such conditions, it now becomes possible to distinguish individual atoms. As the tip passes over an atom at constant height, the tunneling current will be slightly higher when it is over the center of the atom due to the slight change in proximity. Through computer analysis, this signal can be extracted. The raw data is then converted into false color images for us to interpret, such as these shown here. On the left is an image showing deposits of silver on top of a terrace surface of palladium. On the right, and at 10 times the resolution, is shown the outer layer of a lattice of silicon atoms. These are only visible to us thanks to the technological breakthroughs that have enabled the scanning tunneling microscope.